Dear students, after studying this module, you shall be able to know the importance of normal, medium and large carbocyclic and related compounds. Design the synthesis of 5 and 6 membered ring compounds and their derivatives. Design the synthesis of medium and large ring compounds and their derivatives. The carboxylic compounds have and going to play a very important role in chemistry. The interest towards macrocycles have increased due to wide applications. The development is mainly due to their fascinating structural symmetries and new stereochemical aspects. They are also helpful as building blocks in supramolecular chemistry. The saturated alicyclic compounds have a general formula of CnH2n, same as that of an alkene, and are isomers of alkene. They do not have double bond but possess a ring structure. Monocyclic compounds have been classified on the basis of number of carbon atoms in the ring in the following way: small rings 3 to 4 carbon atoms, common normal rings 5 to 7 carbon atoms, medium rings 8 to 11 carbon atoms, and the large rings greater than 12 carbon atoms. The carbocyclic rings are present in many natural product compounds. For example, paclitaxel is a plant derived terpenoid. This is a multi-ring structured compound and possesses 4, 6 and 8 membered rings. As can be seen from the given structure, the varied different sized rings which are present in the given compound. Let us look into the synthesis of the normal ring compounds. Starting with the synthesis of cyclopentane. The retrosynthetic analysis approach of cyclopentane is shown here in the figure. The functional group interconversion shows that the cyclopentane can be obtained from cyclopentanone, which can further be obtained from 2-oxo-cyclopentane carboxylic acid ethyl ester. The carbon-carbon disconnection of 2-oxo-cyclopentane carboxylic acid shows that this can be obtained from diethyl hexane dioate. As can be seen here in the schematic diagram, the retrosynthetic approach from the cyclopentane to diethyl hexane dioate. The cleavage of the compound, firstly the decarboxylation takes place, then the retrosynthetic analysis shows how the cleavage of the ring takes place and leads to the initial product which could be worked out as a starting material. Let us look into the synthesis of cyclopentane. It is synthesized from diethyl hexane dioate using Dickmann condensation on the basis of retrosynthetic analysis. It is shown here in the figure. As can be seen here in the step 1, the diethyl hexane dioate on reaction with the base forms a corresponding anion, which undergoes cyclization followed by the ethoxide ion removal to form 2-oxo-ethyl cyclopentanoate, which is shown here as the structure number 3. In the step 2, 2-oxo-ethyl cyclopentanoate, which is the structure number 3, upon hydrolysis with an acid forms 2-oxo-cyclopentanoic acid, as shown by the structure 4. The structure 4, which is 2-oxo-cyclopentanoic acid, on further heating undergoes decarboxylation and forms cyclopentanone, shown as figure. The cyclopentanone then undergoes Clemmensen reduction using zinc, mercury and amalgam and HCl and forms cyclopentane. This cyclization and the decarboxylation leads to the formation of cyclopentane ring. The synthesis of cyclohexane similarly can be traced by the retrosynthetic approach as given in figure. The functional group interconversion shows that the cyclohexane can be obtained from cyclohexanone as shown in figure, which further can be obtained from 2-oxocyclohexane carboxylic acid ethyl ester, which is given in the figure. The carbon-carbon disconnection of the 2-oxocyclohexane carboxylic acid as shown in figure 9 shows that this can be obtained from diethyl heptane dioate. The synthetic approach for the cyclohexane is as follows: using diethyl heptane dioate by Dickmann condensation in this step 1 leads to the formation of the further compounds. The diethyl heptane dioate on reaction with the base firstly forms a corresponding anion, which undergoes cyclization followed by the ethoxide ion removal to form 2-oxoethyl cyclohexanoate. 2-oxoethyl cyclohexanoate upon hydrolysis form 2-oxocyclohexane carboxylic acid by the loss of the ethoxide ion. 2-oxocyclohexane carboxylic acid on heating undergoes decarboxylation and forms cyclohexanone as shown in the structure number 8. The cyclohexanone then further undergoes the Clemmensen reduction using zinc mercury amalgam and HCl and forms cyclohexane. All these can be very well seen depicted here in the schematic diagram of the figure. Synthesis of cyclohex 4-ene 1,2 dicarboxylic acid. Retrosynthetic analysis and the approach of cyclohex 4-ene 1,2 dicarboxylic acid is shown here in the figure. The disconnection approach explains that the cyclo addition of diene and ene can build a cyclohexane ring. As can be seen, the cleavage of 2 carbon-carbon bonds take place, leading to the formation of a diene structure and an oic acid being splitting out as a second fragment. Synthesis. Cyclohex 4-ene 1,2 dicarboxylic acid is synthesized from 1,3-butadiene and eth 1,2 dienoic acid using Diels-Alder reaction as shown in the figures. When buta-1,3-diene and eth 1,2 dienoic acid are heated, they form the cyclohex 4-ene 1,2 dicarboxylic acid. Synthesis of medium and large ring compounds. Figures show the general retrosynthetic and synthetic pathways for design and synthesis of medium and large ring compounds. The retrosynthetic analysis of carboxylic ring compounds possessing medium to large rings is given in figures. The compounds can be synthesized from aliphatic diacyanides. The functional group interconversion FGI on carboxylic compound 16 shows that it can be prepared from the compound of the type 17. The compound 17 can be obtained from 18, which on carbon-carbon disconnection gives the synthon 19. The synthetic equivalent of synthon 19 is the diacyanide compound 20. It is shown beautifully here in this given schematic diagram. The synthesis and the synthetic pathway of the carboxylic ring compounds possessing medium to large rings is given in figure. These compounds can be synthesized from the aliphatic diacyanides through intramolecular condensation of aliphatic diacyanides. In the step 1, the aliphatic diacyanide in the presence of a base gives a carbanion by the abstraction of a H ion, which is stabilized with the metal ion. In normal cases, it can be a lithium metal. In the step 2, the carbanion 21 undergoes the cyclization to give the carbocyclic ring 22. Step 3 involves the carbocyclic ring undergoing acidic hydrolysis, where carbon double bond NH gets converted to a carboxylic group C double bond O and CN gets converted to an acidic moiety, which is compound number 17. In the step 4, the decarboxylation of the compound 17 gives a cyclic ketone 23, which can be further reduced to cyclic alkanes via Clemmensen reduction using zinc mercury amalgam and HCl. It can be seen here how the different steps take place by the use of different reagents and the different mediums, following the stabilization of a carbon ion using a metal ion, hydrolysis, decarboxylation, and finally the reduction leading to the formation of a final product, which is a medium sized ring structure. Synthesis of 2-methyl cyclohexane 3-enol represented by structure number 24. It can be seen that the carbon-carbon cleavage takes place, leading to the formation of a keto structure, which in turn finally leads to the formation of the synthons. In this case, the allyl silane based strategies have been utilized to build up the cycloheptane derivatives. The intramolecular cyclization of functionalized allyl silanes has been utilized for the synthesis of 7-membered hydroxycycloalkenes and oxycycloalkenes. The functionalized allyl silanes 26 has been achieved from the allylic alcohols represented by the structure 27. The other possible methods for the synthesis of carbocyclic compounds include expanding or contracting as existing ring. Using these methods, it is possible to access the structures that would be difficult with the single cyclization reactions due to slow rate of formation. The expansion of rings is usually done either by migration or insertion or opening of a bicycle to lead to the formation of a single larger ring. To summarize, the monocyclic compounds have been classified as small rings 3 to 4 carbon atoms, common or normal rings 5 to 7 carbon atoms, medium rings 8 to 11 carbon atoms, and large rings with the carbon atoms greater than number 12. Cyclopentane is synthesized from diethyl hexene dioate using Dickmann condensation. Dickmann condensation is also being used for the synthesis of cyclohexane. Cyclohex 4-ene 1,2-dicarboxylic acid is synthesized from 1,3-butadiene and eth 1,2-dienoic acid using Diels Alder reaction. The general retrosynthetic and synthetic pathways for the design and synthesis of medium and large ring compounds have been discussed. The allyl silane based strategies have been utilized to build up cyclopentane derivatives. The expanding or contracting an existing ring method can also be employed for synthesis of the carbocyclic rings.